Good afternoon to everyone present here. Myself, Kaustubh Karnataki from FluxGen Engineering Technologies Private Limited, Bangalore. As a system design engineer, we present to you our analysis on comparative and statistical analysis on electrification, co-authored by Mr. Ganesh and Mr. Mitavachan. So as the topic goes, solar photovoltaics. So everyone over here are very commonly acquainted with solar photovoltaics as solar panels, wherein sun's radiations have been converted into electricity. Now, people in the energy sector will also be knowing about microgrids. So a microgrid is a small scale grid which runs independently or runs in conjunction with the central grid. So what is the solar photovoltaic microgrids? Something wherein power generation is carried out by solar photovoltaics and then distributed among the given particular area. So next line is an eco-friendly alternative for remote electrification. So as environmental impacts are concerned, we are going to discuss about how a lighting source, apart from renewable energy, we will be considering conventional energy and their impacts on environment. So just to add one interesting point, the current status of electrification in India, the CEA, Central Electricity Authority of India, reports about 25,722 villages in India are yet to be electrified. They are totally out of the central electricity grid. Now with the dream of government in connecting all the places to the central grid, which is economically non-viable and non-feasible. So FluxGen Engineering Technologies works on renewable energy systems, and we have a vision of encouraging renewable energy systems, making it more economically viable and engineering-wise reliable. So, walking towards this vision, we investigated a place called Mendel. This place, Mendel, is inside a reserve forest area in Belgaum, a North Karnataka region. The interesting facts about this village area is, it's not at all connected to central electricity grid because it's inside a reserve forest area, and according to the Indian Forest Act, penetration of central electricity grid inside the reserve forest area is prohibited. Apart from that, the nearest available electricity grid towards this village is about 5 kilometers, and this place is situated in between a hilly terrain which is in about a radius of 5 kilometers surrounded with trees, and so even the motor transport to this place is very much difficult. So we come up with analysis to electrify this village. How can we say that renewable energy can help to electrify this? Let's go step by step. So we define an objective. An objective is to define a effective lighting source. So we need to consider a few parameters while defining this objective. So let's take an sample case study. So a village is inside a reserve forest area. Let's consider there are about 25 houses in that village. Each house has 4 rooms of 12 meter square area. Again, as we saw the example of Mendel, the nearest central electricity grid is 5 kilometers away. And here we are going to consider only lighting loads for now, because we have to have fair comparison between the conventional sources, primitive sources, and now the renewable energy sources. So let's have a look at what are the possible methods of lighting. So the most primitive method, a kerosene lamp, which is also a fuel-based lantern, and the most primitive method of our lighting source. Next we will be having the central grid extension, and then there's something known as standalone AC solar PV system. That's standalone AC solar photovoltaic systems. So what are the standalone systems? Here we observe in many places there are independent rooftop solar panels, independent inverter batteries being used, and energy is consumed individually by particular houses. So this we can define as a standalone AC solar photovoltaic systems. So there comes the next, that's the AC microgrid solar photovoltaic systems. So here, as the picture depicts, we have a collection of houses or town, and we have a solar plant garden which is going to be collectively powering and distributing energy. We have a central inverter and central battery bank. So let's see who is efficient, and we are going to analyze about the quantitative perspective, the economic perspective, and also whether it's feasible or no. So these are the analysis we are going to look after: quantitative, economical, and environmental impacts. So now let's define a requirement. Given a village, we require per day 2 hours of lighting. Now a suitable illumination of 100 lux. Lux is lumens per meter square. So what is this lumens and lux all about? So just to give a brief idea of what is this lumens, if you consider this room, how much is the lumens at this point? So if I consider this plane, there's an app which will give you the exact lumens per meter. So if I consider in this plane, it's 31 lux. If I consider exactly below the light, it's 54 lux. So you can say if in this plane, we have a 54 lumens per meter square of light available. It's defined that for reading and daily operations, 100 lux of light is required and is satisfactory. So therefore, now we are considering 100 lumens of satisfactory light to be provided, and then illumination per house. As we have defined a room of 12 meters square with 4 rooms, for per house it comes down to 4800 lumens. And next, now equivalent electrical load. If you consider that much amount of light, how much of electrical load we need to consider? So assuming this a term known as efficacy for any lighting source, electrical lighting source. Efficacy is defined as lumen per watt. In 1 watt, how much of intensity is being generated by the lighting source. Then considering the CFL bulb power wattage required per room for a given area and for a given lumens, it comes to about 25 watt. And now considering the whole village, 25 watt per room, 4 rooms it comes to 100 watts, complete village, it will come to 5 kilowatt hour per day considering 2 hours of lighting. 5 kilowatt hour per day is the energy consumption. So this is our basis of the requirement, and we will design our statistics and comparative analysis taking each lighting source one by one. So first let's start with kerosene based lamps. There are experiments performed in Berkeley laboratories wherein simple kerosene lamps are considered and the luminosity is measured. So according to the report, they say 8 lux of light is being produced by the lamps. Now to provide 100 lux of light, as we discussed 100 lux of light, that's the primary requirement, we require per room of 12 meters square about 150 kerosene lamps, and for a house it will be 600 kerosene lamps. Imagine just to generate 100 lux of satisfactory light, we are using 600 lamps per house. So this is the quantitative analysis. Now rate of fuel consumption. Let's come to what is the economical analysis of it. Now again to the report we see that the rate of fuel consumption is 0.01 liter per hour according to the report. Now quantity of kerosene required for 600 lamps per day comes to 12 liters, considering 2 hours of usage. And the kerosene cost in the current market is rupees 48 per liter. Here I would like to take a point that consumer pays 15 rupees per liter, and the complete other amount, that 68.75%, is being subsidized by the government. But the overall cost for kerosene is about 48 rupees per liter. Now the total expenditure on the kerosene lamps for the given village for lighting for 2 hours, considering that much of light amount required, it comes to about 52.56 lakhs per annum. And it's going to be continuing. It's not that it's one-time investment. It's 52.56 first year, second year the same. Now comes the environmental impacts. So energy density of kerosene is a constant, that's 33 megajoules per liter, and kerosene emission factor is taken to be 0.068 kg CO2 per megajoules. If we do this analysis, the amount of CO2 released, and that too as an indoor pollution, is about 273 tons per annum. 273 tons per annum. Now just to give a brief idea of what this 1 ton will be, 1 ton CO2 is about burning about 322 liters of diesel. 322 liters of diesel. And also to compensate a 1 ton of CO2, you need to grow 15 trees, and that should be live for a year. Now next is the next option, that's central grid extension. As we have discussed, the central grid is about 5 kilometers away from the village. So distance 5 kilometers, Now, government has defined that the safe intervals between the poles to be used should be strictly 65 meters or less. So we consider 55 meters as the safe way. Consider a 5 kilometer stretch. We require about 90 poles in this. Now, as we discussed, we require 5 kilowatt hour of electricity generation. So, according to the Green Report of coal analysis in India and the carbon dioxide release, we have 1.6 tons of coal required to generate a 5 kilowatt hour per year. Now, economical. We have to consider for a 5 kilometer stretch a 11 kV line, transmission line, and cost per kilometer comes is reported, is quoted to the government always to be 0.35 million. Here the equipment costs are additional, in the sense the transformer, step up, step down, all are additional. Only the transmission line costs come to 0.35 million rupees. And considering the lighting loads and network cost, if we want to electrify this village by central grid penetration, we will require 18 lakhs of installation costs. Apart from that, an operational cost like the user has to pay per year again 20.5k. That's the operational cost for a given year for that village, apart from the installation cost. Now let's have the environmental impacts to be considered while penetrating this central grid. So government has defined if there is a requirement of central grid penetration into a forest area, the right of clear way path should be minimum 7 meters and the tree to conductor clearance should be 2.6 meters. So imagine if you want to extend this onto a 5 kilometer stretch, it should be like a forest fragmented for the way for the central grid to penetrate. And that route should be continuously monitored for any short circuits or fire hazards to prevent forest fires. So these are the heavy environmental impacts we can observe in this case for the central grid penetration. Now the CO2 emissions by 1.6 ton, there's a formula to calculate the quantity of CO2 being released by the emissions due to the central grid being electricity generated to central grid is, it comes to about 152 kg per annum. See where the kerosene was, and now it's 153 kg per annum by central grid extension. Here I am considering the conventional grid electricity. Please remember, here we are not considering the transmission distribution losses and also the deforestation emissions. I would like to tell you, we all know that plants absorb carbon dioxide, but there is a fact that whenever they die on their own or they are chopped off, the stored carbon dioxide is immediately released into air. Now to penetrate this central grid, 5 kilometers of stretch, you should imagine how many trees have to be chopped down and what will be the carbon dioxide released. So that's not being considered, that will be additional to this. So now we spoke about kerosene lamps, we spoke about central grid penetration. Let's talk about individual solar photovoltaic lighting systems, that's standalone AC solar PV systems. So the quantitative analysis, as we discussed, 25 watt of CFL will be used per room, 100 watt for a house, for 2 hours it comes to 200 watt hour. It comes to 200 watt hour. Now considering the inverter efficiency, as we are using a low power inverter, we have the inversion efficiency to 50% and MPPT, that's a maximum point tracking, to be 75%. We come to a battery requirement per house for that electrification of 200 watt hour or 50 ampere hour battery, and the solar panel capacity required will be 50 watt peak per house. If we come to economical analysis, assuming the current market rate of inverters, it's about 3.5 kilo, 3,500 batteries and solar panels respectively, then we can estimate per house the system will cost you around, that's per house, and then considered as whole village, it will cost around 3.675 lakhs. And cost per operational cost will be nil because it's a solar PV system. Then environmental impacts. As reported by this UK Parliamentary Office, it says that 60 gram of CO2 will be released per kilowatt hour in manufacturing solar panels. And then thus we define the carbon footprint to be 300 grams. It's only one time release and thereon it's free, it's no. Then AC microgrid systems, it's considering the complete village of 5 kilowatt hour. And now again, as we are using a high power inverter, it has a better efficiency, 90%. And solar hours in Bangalore it's considered to be 5 hours. And now the microgrid battery capacity, if we calculate, comes to 1000 Ah, and solar panel capacity comes to 1100 watt peak. So coming to economical analysis, just the total cost, if you use a microgrid to electrify this village, it will be 2.62 lakhs, and again operational costs will be nil. Carbon footprint, as discussed, it's similar. A solar panel manufacturing, it's just 300 grams at the manufacturing cost. Just quick comparison, that when we use individual solar light system, this is very important. You require a battery capacity of 1250 Ah for same power. It's 1000 Ah in terms of microgrid. That's the 1250 watt peak in case of individual solar lighting, considering the complete village. It's 1100 watt peak for microgrid. 3.675 for this, and it's 2.62, difference of about a lakh. And now we are coming to at the end. The main thing is the comparative analysis. So if we consider our village to be powered by kerosene lamps, that's one. Then if we consider how many villages can be electrified with similar power, it comes to 3. So it's like if you power kerosene lamps by 1, it will be thrice. In case of standalone it's 14, and in case of microgrid is 20. And similar for CO2, kerosene will be too high. So we consider central grid extension to be 1. Then the CO2 release, similar in case of solar panels and the technology, just 500. And here that's it. And here we have implemented the Mendel photo, as we said. So this is the 2 kilowatt microgrid which we have implemented, and we are producing an AC solar photovoltaic microgrid. In fact, we have a model exhibition which we have already exhibited, and we would like to even suggest you to have a look over it once you are done with the session. So thank you.